example here talking about the heat capacity of liquids. And you can tell by my picture, I'm specifically going to use water in this example. Okay? So, let's do this example from kind of working backwards. All right? So let's first start with liquid water. We know the specific heat of water is 4.18, I'll say 4.184 joule per gram per Kelvin. We know that's the same as joule per gram per degree C. Okay. What if I now want to convert this into joule per mole? Well, I know water is about 18.01 grams per mole. So when I do that with 4 sig figs, okay, I get 75. Oops, let me make sure I hit that in right. Yes, I get 75.35 joule per mole per K. Okay? And so we'll back up and we'll recognize that, right, heat capacities, CV, are some constant times R. Okay? So I'll put in some constant C times R. So for a solid, it's 3R. For a monatomic gas, it's 3/2 R. For a nonlinear molecule gas, it's also 3R. So what about for liquid water? Okay. Well, if I know that this is the specific heat, 75.35 joule per mole K, or excuse me, rather, the specific heat is 4.184 joule per gram per Kelvin, and I know the heat capacity is this value, 75.35 joule per mole K, then what is this constant? Well, divide 75.35 by R, okay? So let's do that, okay? So I'm gonna divide that number by 8.314. This is awesome. I get 9.06. Now, some of you are like, why is that awesome? Why is that significant? Well, it's damn close to the whole number 9. Damn close, okay? And the reason why it's not exactly 9 is because this is the equipartition theorem. So what's significant about the number 9? Okay, well, if CV for liquid water is 9R, how many degrees of freedom does that correspond to? Well, it would have to correspond to 18 degrees of freedom, right? 18 1/2 R gives me 9R. Where does that 18 come from? This is awesome. Here's the water molecule, okay? There's a hydrogen, there's an oxygen, and there's another hydrogen, okay? And then we know from this picture, right, that it's in this like really complicated, always changing hydrogen bonding network. So hopefully I've drawn this thing big enough to make sense out of this thing. Actually, I think I'm gonna pick on, can I pick on one of those? No, I need to draw my own to make this. Okay, I'm gonna draw this bigger. There's my very cartoon, crappy looking water molecule. Okay, so I'm gonna do a different color. And let's make a coordinate system. So we know that this hydrogen, it can move forward, backward, left, right, up, or down. Okay? And so that motion, so imagine like my torso is the oxygen, right? And each of my hands are the hydrogens, right? We know water can vibrate like this symmetrically. We also know it can vibrate like this asymmetrically. We know it can undergo the rocking motion or the bending motion, okay? So all of those give us this three-dimensional coordinate system on each one of these atoms. So each one of these atoms are really free to move forward, backward, left, right, up, down. Forward, backward, left, right, up, down. That's 6 degrees of freedom per atom, 6 DOF per atom, and there's 3 atoms in the water molecule, giving us 18 degrees of freedom, giving us 9R for the value of heat capacity. And if I go and calculate, and you know, I did this backwards and we got 9.06. So if I go the other way, suppose I just calculate 9R, 9 times 8.314 gives me 74.826, okay? And then now if I divide that by the molar mass of water, 18.01, I get 4.155. That's really damn close to the specific heat capacity of water, the measured heat capacity. So obviously there's, you know, this model doesn't account perfectly for that. And we should also recognize with something as chaotic as liquid water, right? It's not so simple to just say like, well, assume each molecule moves like forward, backward, left, right, up, down, and then just say that times 6, right? But it's damn good. It works really well, okay? And so this model will fail for much, much larger molecules because the interactions become a lot more complicated than just up, down, left, right, forward, backward, okay? However, for these simple molecules, for liquids, this works really well. For the solids, this also works really well, okay? So for all liquids, or for the simplest liquids, it's the specific heat capacity, and then kind of work backwards into the degrees of freedom, which for water is easy to do. For other more complicated molecules, not so much. For solids, 3R. 3R for the heat capacity. And that is, of course, above the Einstein temperature, right? And then for gases, 3FR for monatomic gas, 5FR for linear molecule, 3R for nonlinear molecule heat capacities, okay? I think that's a pretty good place to end it. And we'll get into talking about enthalpy in the next lecture. All right, folks, thanks for tuning in.